Hello. So next what we are going to do is talk about a different type of machine learning problem called clustering. And I understand some of you already know about it, but it's essentially how we cluster or group different objects that are similar to each other together so that we end up with these groups that have uh, high similarity within each group, but these are significantly distinct from other groups. It's different from classification because in clustering we will not have access to what is the actual class of each of these examples for training even. And whereas in classification we know the target class or the true class of a given example. So that's the difference between them. One of them is what is called supervised. Classification is supervised because we have a supervisory signal, the class label in this case, that we can use to group things, right, into classes. Whereas in clustering, we do not have a supervisory signal. There is no information on what groups these examples, a particular example should fall in. All you are given is a set of features for a given example, and that's pretty much it, nothing else. So all you get is a simple data matrix X, and you are going to use the similarity between, or you have to use the similarity between different features across different examples to essentially group examples that are closer to each other. Okay, and you think about it based on this visual that I'm gonna put. I think it's gonna give you a better idea. Let's say we've got two features, x1 and x2, and we say that we want to divide this data set for which we know these two features. So there's a bunch of examples. That each example shown in a blue dot over here, right? Like this one or like this one, for example. What we want to do is we want to group these examples into three groups so that each of those groups is more similar, or examples within a particular group are more similar to each other than examples in other groups. Okay, so this is a clustered output. So this is what essentially clustering does. So this is the impact of clustering. You give it just the feature values x, which can be number of examples can be n, and each example can be expressed in d dimensions. You give that as input, and what you get at the output is for each of those examples you get a clustered output. Okay, so these group of examples, these ones over here, fall into a blue cluster, these ones into the green cluster, and these ones into the red cluster. Okay, so all of these examples have been grouped based on similarity of how of their similarity to each other. Okay, and the number of clusters can, if we increase the number of clusters, we are going to get a more finer fragmentation of this particular data set. But I think you get the idea. The goal of clustering is to essentially take an unsupervised or take a feature matrix and assign groupings to each of those examples. Okay? One of the most commonly used algorithms for clustering is called Kmeans algorithm. What it does is that it takes in a data matrix X and it generates groupings of examples within each cluster. So if you have an example of a data matrix like this one, in which you have n examples, each of them expressed in d dimensions, what is it's going to do is it's going to give you two things. One of them is going to be what is the cluster ID of each of these examples. So which examples fall in cluster 0, which example falls in cluster 1, and so on. And it's also going to give you cluster centers or cluster exemplars, as they are also called. Okay, so those are going to be the representative examples of each cluster. At the same time, at the input, you also need to specify how many clusters you want. You can have, let's say, k is equal to 3, and that's why it's called k-means, just like k nearest neighbor. Here, what we specify is how many clusters do we want. Okay, and the output I've already discussed, that is the assignment of each example to a cluster as well as getting cluster centers. Okay, I'm not going to go through the algorithm first. I'm going to go through how it looks geometrically. Let's say you've got these diamonds, black diamonds that you see over here, right? These are your data points, and this is a scatter plot. Each of those examples over here, like this one, for example, has two features. The first feature, let's call it x1 along this axis, And then you've got another feature that's along the vertical, which is, let's call that x2. So for each of those examples, we have their feature representation. Now, let's say if I want to group this data into, let's say, 5 clusters, or k is equal to 5, then what I do is I initialize 5 random vectors. I'm going to call them C1 through C5. Okay, and each of these vectors, C1, C2, C3, C4, and C5, are going to be two-dimensional. And I'm just going to use different colors to represent them so that we can see where they are. So because I did the representation, the initialization of these vectors, these two-dimensional vectors, randomly, we can say that these end up as, we can show them as crosses, and these end up at the locations where you see them in this particular plot. Now, the next step that we are going to do is we are going to find, for each of these diamonds, we are going to find which of these exemplar vectors, as I'm going to call them, or these cluster centers that I have initialized completely randomly. And I'm going to find out which cluster center is the nearest to a given example. So for this example, we know that this red point, this red cluster center, is actually the closest one to this one. So I'm going to color this point red, and that is going to indicate that I've assigned this particular point to the red cluster. And I do that for all of my examples in the dataset. And once that is done, so once we've done that, this point is going to be assigned to the red one. This point is going to also be assigned to the red. This is also going to be red. This is also going to be red. So we end up with a bunch of different points that belong to different clusters. And we know each point belongs to exactly one cluster based on nearest neighbor rule, right? The next thing I do is I find the mean of all the points that are within a certain cluster. So if, for example, all of these points, these ones are red, then what I do is I calculate the mean along the first feature and the mean value of the second feature for all of these points. And then what I do is I move this red dot, or this red exemplar, or this red cluster center, to the mean of those points that belong to that red cluster. And I do it for all the clusters that I have. Okay. And if I do that, this is what I end up with. Okay, so do you notice the difference between the two? So that we essentially move these cluster centers to the means of those clusters. So we end up with a new cluster assignment. Then what I do is I reevaluate which examples are the closest to which cluster center. Okay. Now I see that this example is red. This one, for example, this particular example is red, but it's closest to this blue point. So I do a reassignment of these cluster centers, and I redo the center assignment step based on the mean value. We do it again for all of the cluster points, and notice the difference between this plot and the next one. You see all these points within this cluster over here have now been assigned to this blue point, because those were most of them were actually closer to this blue point. I keep on doing that until these cluster centers stop moving. Okay, so once we achieve a steady state of these cluster points or these cluster centers, we stop the algorithm. Okay, so you can think of it as a loop, right? We initialize cluster centers randomly based on how many clusters we want. Then what we do is we reassign our data points to these clusters. We calculate the mean of the clusters, or the data points in the clusters for each of the features. We update the cluster centers to those mean points, and then we repeat this process until we reach a steady state. This is all that's discussed or given in this code as well. We initialize k exemplars, which are indicated by mi. I had indicated them or denoted them by ci for examples, to k random, xt. And then what we do is we repeat For all the training data points that are given to me, I find which of these exemplars is the closest to that, and based on that, I update that exemplar, and I keep on doing that until I converge. At the end of this process, I end up with two things. I end up with a cluster assignment of each point to a given cluster, and I also end up with these cluster centers. Okay, so that's really nice. This is what we end up with. Okay, and this is a very simple algorithm. All you need to do is to define, give it your data, and define how many clusters you want, right? And then it's going to take care of the rest. However, even simple things can hide so it's really simple, but it's really beautiful at the same time. And there are a bunch of moving parts that people typically ignore. So for example, how do I define the nearest? That's going to require the calculation of a distance metric, right? So what metric do I use? Do I use L2 distance? Do I use L1 distance? Do I use another distance, etc.? Like, what is the distance metric that I want to use? And how does it fit in with the concept of structural risk minimization? Now, there's a proof that we are not going to go through, but what it essentially says is the following: that for a given bunch of, if you have a given data set X that has n points, and each of those points in d dimensions, and you want to get k different clusters out of it, the cluster points that you get, the k points, the exemplar points that you get, M1 to M5, based on this algorithm, are actually the ones that optimize or give you the least quantization error. Now, what is quantization error? I'm going to explain to you. It's really easy. You've got all of these yellow points over here. You see them? And they have a cluster center assigned at this position X. Let's say if I replace all of these yellow points, the original diamond points, with this X, then you can say that we lose a bit of information, right? We have replaced each of these yellow points with this X. So essentially all of these points end up at this location, right? So the amount of information, or the amount of variance, or the amount of distance I lose can be quantized, right? So what we are doing essentially is quantizing each of these points to a single point, right? And this is going to be the amount of distance or deviation or difference or loss that we lose if I replace this diamond point with this one. So you can think of this optimization, or this clustering method, in terms of optimization. What we want is, we want k cluster centers, so that if I replace all of the data points with those cluster centers, I end up losing minimizing the quantization error, that is the distance, if I replace this particular point with the cluster center. And there's a proof that we haven't done that, and that shows that this K-means algorithm is pretty good actually at ensuring that we end up with a low quantization error. Okay, so that is the loss function. Remember, our SRM required us to have a loss function. So the loss is quantization error. But where does regularization go? The second component of SRM. And that is dependent upon two things in this case. Remember, regularization, the simple concept that we've talked about is things shouldn't change too quickly, right? If I change the value of k, if I pick k is equal to 1, then everything is in the same cluster, right? If I take the value 2, we end up with 2 clusters, right? The maximum number of clusters that I can take for a given data set is going to be the number of examples that I have in that cluster, right? But that makes it very poorly regularized, because a small, simple change, let's say from this example to this example, is now going to give me a change in my cluster assignment. So this k thing is directly related to regularization. Okay? So think of regularization and the loss function for this, and you would be able to write out the formulation for a mathematical formulation for k-means in terms of SRM as well. Okay, so that's how it relates to our SRM understanding, right? So the choice of your k value controls the regularization, and at the same time, the choice of your distance metric also has an effect on regularization. Okay, and you can get different clustering based on the distance you used. Once we have obtained a clustering for a given data set, like this one, for example, we can cluster unknown point, like or novel points or test points. Okay, so for example, if I have this point that occurs over here, probably it belongs to this yellow cluster, right? So you can divide this uh, feature space into, you can make lines that separate out different classes, right? You can, I'm not doing a very good job here, but you get the idea, I hope. Okay, and these are the different areas where each of these points, um, so any point within over here will belong to the yellow cluster, and any point within this region is going to belong to the blue cluster, and so on. So this is, if you take a look online on what are Delaunay triangulations or what are Voronoi diagrams, you can relate them to this concept. So they ensure, they give you an area or divide this particular feature space into different cluster areas. Remember, we discussed the objective of classification was also to partition the feature space. Clustering does the same, except that in classification, we are given a supervisory signal on how to cluster this feature space. Whereas in clustering, we don't have that supervisory signal, and all we have is the information contained within our features, and we use that information to identify how to partition this feature space. Okay, the effect is similar at the end, and we can obtain cluster assignments for each of these points, but it's the way these two things function in training that is different. Okay. Okay, so I hope you have a good understanding of K-means clustering. There's another algorithm which is called hierarchical clustering that we are going to talk about very briefly. So if you think about clustering, all we have done so far is that we don't even need essentially features for a given example. All we need is how far away an example is from another example, or we need a distance. And once we have that distance, we can apply k-means and we can find these exemplar or these points, and we can essentially assign these cluster centers to unknown points. Okay, hierarchical clustering is a very interesting method for doing clustering. So not only does it give us clustering, but it also, and you can get cluster centers out of it as well, much like the k-means method, but it also gives you a hierarchy of clusters. Okay, so I'm going to give you a single dimension example just before going into the details of this method. So let's say we've got these data points. It's a single feature. So each example is a single feature example, and the total number of examples is 1, 2, 3, 4, 5, 6, 7, 8. So because there is only a single feature, we can start thinking of grouping different examples based on how close they are. So 1 and 2 are the closest examples within this data set, right? So 6 and 7.5, for example, have a distance of 1.5, whereas 1 and 2 have a distance of 1. So what we do is that we connect these into a single cluster. Okay. The next step we do is we do it for the next closest pair and so on. So we end up with these 2 points, and then these 2 points, and then these 2 points. And as you can see, the way we've connected this, the height of these black lines is indicating how far away these two examples actually were, right? And if we can do it for 1D, we can probably do it for 2-dimensional data. Let's say if you have 2 features, we can apply the same principles. You can have, we can calculate the distance between 2 examples based on 2 features as well, and then we can do the same thing. So it doesn't really matter how many dimensions you have right now, okay? But what we are doing is the height of the black lines is proportional to the distance between these examples. Okay. The next thing we do over here is we now need to connect these clusters or the subclusters that you've obtained. Which clusters do you think we should connect? And if you want to pause the video and give an answer, that would be nice. If we think about this particular data set, we can see that we should be connecting the clusters 1 and 2 to the cluster that is formed by 6 and 7.5, because these are going to be closer together in comparison to other clusters, and that's what we can do next. However, there are different strategies that you can use. For example, if you calculate the distance between these two, you can connect these two first, depending upon whether you want to use the minimum distance between two things, or you want to use the maximum distance between two things, or you want to use the average distance between two clusters that you have over here. So that's going to change the way you do your clustering. Let me illustrate that. So let's say you've got these 2 points. If you want to use the minimum distance between this cluster, between this cluster and this cluster, then the minimum distance between them is going to be between these 2 points, and that is going to be 4. And then the distance between these 2 points is going to be 10 minus 7.5 is probably going to be about 2.5, right? Similarly, you can calculate a minimum distance between these two examples or these two clusters, and that's going to be 5. So the minimum distance between, if you use the minimum distance criteria, or as it is technically called, the minimum linkage criteria, then what we should do is we should connect these 2 points. We can also use the average distance. So for example, we can calculate a distance of 1 to 6, and we can calculate distance of 1 to 7.5, the distance of 2 to 6, and the distance of 2 to 7.5. And then we can, if that distance comes out to be closest, all of these pairwise distances, we can use that. So that linkage criteria determines essentially how we go from clusters of examples to bigger clusters of examples. Okay, so if you use minimum as the linkage between these two, we should be connecting these two clusters. Okay, and again, the height of the black lines is proportional to the distance or the minimum distance between these two clusters. Okay, and we keep on doing this until we are left with only one cluster, right? So this is the algorithm which is called agglomerative clustering or hierarchical clustering. And what it essentially does is it takes in our examples as features of our examples, applies a linkage criterion on them, and does it recursively to end up with these hierarchies of examples. So this plot over here, which is called a dendrogram, shows how or what is the structural organization of our data. Now this tells me that 1, 2 are more similar to each other than 6 and 7.5, and 10, 2 are more similar to each other than 17 and 20, for example, the examples with features 17 and 20, right? But it also tells me that this bigger group of cluster is more similar to this cluster than it is to this one, for example, over here. And these heights are very informative as well. So if you want to uncover the hierarchical organization within your data, this method is for you. All you need to do is to define a distance metric, define a linkage criteria, give your features, and then you can get plots like this dendrogram, which you can cut at a certain height. So for example, if I cut it at this height, okay, I end up with 3 clusters. There's a cluster comprising examples 1 and 2. There's a cluster comprising examples 6, 7.5, 10, and 12. And then there's a cluster comprising 17 and 20. So you don't need to give the number of clusters you want. You simply need to give a distance cutoff. Okay, so that's the good thing about hierarchical clustering. And we can ensure that the minimum distance between any group of these examples is going to be the maximum distance, the maximum linkage distance between examples within a certain cluster is not going to be greater than the threshold or the distance threshold that I've specified. Alternatively, you can also specify the number of clusters you want. Let's say if you want 4 clusters, you're going to end up with this as a cluster, this as a cluster, this as a cluster, and then this as a cluster. Okay, so this is what you can do with hierarchical clustering. These are really beautiful methods, really simple methods, but very effective, not only for visualization, but for general understanding of your data. I'm going to give you some examples on that. Okay, but before going there are some hyperparameters here as well. You have a distance metric that you need to specify, and you also have a linkage criteria. You can use a cutoff, which is also a hyperparameter that will determine how many clusters you end up with, right? And how does it relate to SRM? That is a question for you. Similar to K-means clustering, this also minimizes a quantization error. And the number of clusters is actually dependent upon regularization, much like it was in K-means, right? So I want you to develop an understanding related to structural risk minimization. Okay. So before moving on, as a test example or a really good visualization and application example of hierarchical clustering, I'm going to give you I'm going to use an example for the SARS-CoV coronavirus. And if you are troubled by that for any reason, because this is a sensitive topic for some people, if you want to skip that, please feel free to do that. There are other applications out there of hierarchical clustering and clustering in general that you can find on the internet without losing any or much of your understanding. But if you want to follow on, let's jump right in. Now remember, hierarchical clustering or even K-means clustering requires us to specify distances between examples, right? So let's say if I got two strings, one of the strings is, let's say, GATTACA, I'm going to call that string 1, and then let's say we've got another string which is, let's say, GATTTCA. Okay. Now I can calculate a distance between these two strings without even going into feature computation, because we can define the added distance between these two strings, and the added distance between these two strings is going to be 1, because if I make one substitution, I can go from this string to this string, because the only difference between them is at this location. Okay, so we can calculate these distances between strings, and this allows us to measure similarity of strings and construct these hierarchical clustering maps for strings as well. Now the coronavirus, or any other virus for that matter, has a DNA or an RNA string in it. And if you can read that string for a given virus, then what we can do is we can construct a hierarchical clustering of these different viruses. Let's say you go to different countries and you isolate different viruses or the SARS-CoV-2 virus there. So you go to China, you get a sample of that, you read out its string, its RNA or DNA string. In case of SARS-CoV-2, it's going to be the RNA string because it's an RNA virus. And once you have that string, you measure its distance to every other example, every other virus in this case, in your collection. Once you have that, you can apply a linkage criteria and you can construct what is called a, and this is nothing more than a dendrogram, right? You can construct a dendrogram, but technically it's called a phylogenetic tree. Okay, because what we are doing is we are doing a phylogeny analysis or genetic analysis, or we are trying to understand the genetic differences between different species. So let's say we got isolate from Wuhan, where the virus originated. Okay, you can compare it to other viruses that have been isolated within that region and at other places. So, for example, there was a virus that was determined in, let's say, the USA, in Tennessee, on 25th of November 2008, in a bat, or in a person, sorry. And we have the sequence for that. We have a sequence for this virus, SARS respiratory syndrome, in Canada, in 2000. I don't think we have the year for that one, but we can isolate different viruses from different regions. Okay. And then what we can do is we can compare these pairwise distances, and we can construct this dendrogram or the phylogenetic tree. And what it tells us, how are these different viruses related to each other? And what this shows is that these two viruses are actually closer. These two viruses, which had been isolated from bats in China in 2017 and 2015, are actually closer to the DNA or the RNA sequence or the genetic sequence of the Wuhan virus in China when it was detected. And this gave rise to the theory that probably this virus came from bats and so on. But but it also allows us to analyze how this virus spread. And I'm going to show you another histogram, dendrogram of how this virus has spread throughout the globe. Okay, and this is an application of the coronavirus of hierarchical clustering to the coronavirus. Okay, so I'm waiting for the website to load up. Okay, so this website, what it allows us to do is it allows us to construct, and if you look at on the left side, this is a dendrogram. It's just laid on its side rather than vertically, and it shows us how viruses isolated in different countries, how SARS viruses or SARS-CoV-2 viruses isolated in different countries are related to one another. Okay, and we can zoom in on the country as well, and we can play it in the form of a time series as well. And that is a very powerful visualization that allows us to understand the spread of this virus as well as the genetic mutations within this virus. The link is in the notes and you are welcome to explore it on your own. I'm just going to play it for the sake of so this is where the virus was first spotted. Originally there was only one strain, and then as it spread, it mutated as well. You can have these different, we can visualize it on the map, but at the same time, what's more interesting for us is the construction of this dendrogram. Okay, so this is just the output of a hierarchical clustering method with some tweaks that allows us to analyze how this virus spread and mutated across the globe. So I hope now you have a better understanding of how these hierarchical clustering method and other clustering methods are useful. They allow us to analyze how things are similar and how things are organized, and they give us very good visualization tools that allow us to make sense of our data and possibly infer more information about, for example, in this case, origin of a virus or properties of different types of clusters in our data set. Okay, so I hope that was useful. Thank you so much.